Yeah. So these three laws. Yeah. The first one is see Ohm's law. Second, third, we do not see the names. Yeah. If I find it, I will put there. All right. The first one, the famous Ohm's law. Okay. The electric current through a conductor. Yeah, let's look at this picture. Okay. Let's focus on these 2 points. Yeah. When we understand Ohm's law, try to focus on these 2 points. Yeah. Between these 2 points, there is a voltage V. Voltage number V. Yeah. Between these 2 points. Then electric current goes through this resistor. This resistor has the resistance R, and electric current I has certain number of ampere. Yeah. So then Ohm's law tells us V equals R times I. Yeah. Very simple, yeah, very famous, very useful. Okay. All right. The first one. Second, the third. Second, inductance. Inductor, so this time we look at 2 points around, yeah, before and after this component. Yeah. This time, yeah, if you look at this, inductance is defined as the ratio of the induced voltage. Induced voltage between these 2 points, there is induced voltage to the rate of change of the current causing it. Current I of t, rate of change I prime, or di over dt. Yeah. So this sentence tells us L equals voltage over that I derivative. Okay? All right. To understand that, you see defined. Okay? So you see defined. Yeah, here I want to explain the whole thing. Yeah. Because you cannot define arbitrary things, right? So when you make a certain definition. So here, we are in physics. So here the context is the physics of electricity context. Yeah. So we should think in physics, not in math. Yeah. In math, when we say definition, for example, the limit, so then we describe the formal definition of the limit. Yeah. But in physics, the situation is quite different from math. Yeah. So in physics, when you make this defined, you may treat it as a definition, yeah, because people may treat it as a definition. But actually, it should be treated as a law, not definition, law, all right? Similar to Ohm's law. Why? The reason is physicists discover some rule, some law by many experiments. Yeah. So physicists, they do experiments, okay? Yeah. With all different coils, components, and all different voltage measure, numbers, and electric current measure, rate of change, do experiments, then take the ratio. Then they notice for the same component, let's say the same component, all right? Then they change, electric current, yeah, because you can change electric current, right? So then you get different induced voltage. But then you take the ratio always constant. That phenomenon should be observed by large number of experiments. Okay? Yeah. Based on that observation, then physicists summarized a law similar to the way to get Ohm's law, how to get Ohm's law. Right? Yeah. So you measure that voltage, electric current, right? Take ratio V over I, you see for the same component, you always get constant. You can change electric current, you measure different voltage numbers, but the ratio always constant for the same resistor component. After you change a different resistor, you also get a ratio, the same number, although that number different, right? But when you change electric current, voltage numbers, ratio, another constant. So that's the way to get Ohm's law. Here, the situation is similar. Okay. Then, the physicists can define, that constant. How about we just define that constant as the inductance? Okay? Yeah, so then based on that, inductance is defined in that way. Now you can write this formula. Okay? Yeah. So this formula actually tells us a basic law, basic physics law. Yeah. So we should understand in that way. Physics, not in math. Yeah, math, so you describe a concept rigorously, right? Like limit, like derivative. Yeah. Yeah. Different. Yeah, the last one, similar explanation. Capacitor, this time. Every isolated conductor exhibits capacitance called self-capacitance. Yeah. Holding certain amount of electric charge, that meaning capacitor. Okay, capacitance. Yeah. It is measured by the amount of electric charge that must be added to an isolated conductor to raise its electric potential by 1 volt. Yeah. Yeah. 1 volt. Yeah. Yeah. So, here, 2 isolated surface, but very close. Yeah. Very close. So then, this device, this component can store certain amount of electric charge. We use Q to represent it. Q. Yeah. Q. All right. This Q, amount of electric charge, has some relation with electric current. Yeah. Because electric current caused by, electric charge. Yeah. So there is that relationship also. Yeah. Yeah. Later we will see the derivative of Q with respect to time t equals that electric current. Yeah. Derivative. Yeah. Okay. Yeah. So we may need that formula later. Yeah. All right. So now here, V equals Q over C. Yeah. So see the capacitance, definition of capacitance, people can measure by experiments, similar to the way to measure inductance and resistance. Yeah. So we have these 3 basic laws. Yeah. So these 3 laws should be enough for us to solve most of our electric circuit application problems. Yeah, in this class. Yeah, pretty much should be enough. Okay? Yeah. So we should get a good basic understanding. So before, later we can solve, so many different application problems about this topic, electric circuit topic. Okay. Yeah. All right. So let's continue. So now we need to solve our first electric circuit problem. It's a simple case, our first case. RL circuit. You know R, you also know L. There is no C here, you see? The first one, we want a simple version, so we do not have that C. capacity, capacitor. Yeah. We don't have that component, capacitor. Yeah. Problem 7. Yeah. Look at this figure. Yeah. E, you know E, right? Yeah. So we call EMF, yeah, electromotive force. Yeah. Here, battery. Yeah. Just, think about a simple battery we put there with constant voltage, 45 volt. Yeah, constant, always constant. All right. Then resistance 11 ohms, ohms 11. Okay. Yeah. L capacitance, inductance 0.1 Henry. Yeah. The unit Henry, H. Yeah. Now the question. Yeah. So let's look at. We need to. Our goal, finding the solution for this electric current I of t function. I of t function. Okay. All right. Assume that, the known information. So I just explained these 3 given data. Yeah. All right. Then the current is initially 0. Yeah. At the beginning, our initial condition, when t equals 0, I of 0 equals 0. A, the unit A. Yeah. Okay. Yeah. Then, under the given information, now we want to calculate. Calculate the formula for that I of t, based on the physics laws. Those 3 basic physics laws still not enough, because here we need to do the modeling, right? Those 3 give us the local description. So when you look at the description of those 3 laws, we always consider 2 points, right? 2 points around one component. That's local. All 3 laws we all look at locally, okay, around the one particular component. That's not enough. In order to do the modeling, we need to look at the whole system. Here, the system, electric circuit, that whole system, globally. We should have a global view. How to describe the whole system? We need some law to cover, some physics basic law, another law to cover the whole system. So let's see another physics law here. Kirchhoff's voltage law, KVL. Kirchhoff's voltage law. It's a global one this time. Covering the whole system this time. So let's look at the law description. The voltage, here we refer to the electromotive force, EMF. There is a voltage number. Okay. The energy, the power. Okay. We need energy to power the whole electric circuit. Okay. So that one equals impressed on a closed loop. Here the closed loop is equal to. There is equality. So left hand side EMF, right hand side sum of the voltage drops. Okay. Electric current pass through one component, there is a voltage drop, right? So we understand that. Voltage drop. Okay? across all the other elements of the loop. Yeah. Here there are two other elements other than EMF. Yeah. This is one element. Yeah. But left-hand side, we use EMF. Right-hand side, we do not include EMF. Yeah. Non-EMF components, right-hand side. But we need to, adding up. Voltage drops from all those components. Yeah. That's the Kirchhoff's voltage law. Okay? So it's a global law, right, for the whole system. Yeah. That's the one we need to help us set up the differential equation. Modeling, our main modeling step. Yeah. With that, now let's set up our main differential equation here. Okay, all right. Before we do that, let's bring up two basic laws or local laws we need to apply. First one, Ohm's law, V equals Ri. Another, V equals L, this one. Yeah. I like to have a name because I couldn't find, from textbook. Yeah, I searched web a little bit. Yeah, if I can find, I like to put there. Yeah, not very well known. Yeah, but it deserves a special name. Yeah. Anyway, all right. Now we are ready to set up the differential equation. E, left-hand side. E, right-hand side. Two components. Yeah. The first one, the order may not be important. Yeah. So order, yeah, because the order may not be important. Just don't skip any component. Yeah. Cover all the components on the loop. Yeah. L times I prime, derivative, I prime. Okay? Yeah. We know with respect to t. Yeah. Variable is t, time t. Yeah. Plus R times I. E, L, I, R, these three numbers are given. We just plug in. Yeah, so we can get a, before we plug in, we may like to write the structure we can see better, right? Yeah, so that's the usual way we write our ODE. Yeah, so we try to rearrange the terms to fit the typical pattern of our ODE. Yeah. All right. Let's plug in the constant. Yeah. So we may like to, because we usually we use YX, right, variable. Yeah. So you do not have to switch, but for people, so you may feel, use our familiar symbols. Yeah. If you use the symbols not quite familiar, so your productivity may not be as good, right? So here, just based on the psychology, okay? Yeah. So think about yourself, based on people's psychology, okay? The symbols matter, okay? Symbols really matter, yeah. So we like to choose the most convenient symbols for us. Yeah. Here, the reason switch because we feel comfortable when we see Y, X, or T things, right? Yeah, usually our formulas using Y, X, or T versions. Yeah. But you do not have to change. Yeah. You do not have to change. You can solve on that directly if you feel your productivity is the same. Okay? If you feel you slow down, so you have to spend more time to understand the format, then probably you like to switch to more convenient symbols. All right? Yeah. So based on my psychology, I feel more comfortable on this version. Okay? Yeah. So let's make the switch. Yeah. After we get solution, we can switch back, right? Yeah. All right. Now we need to solve this differential equation. this differential equation. Yeah. Here, because we just practice that exact form, exact differential form, that technique. Yeah, we just practiced. Okay, so here we want to apply it. Yeah. All right. Yeah, but here I want to make a comment here, because can you make this equation treated as a separable ODE? Easily you can. Yeah, because pretty easy to solve as a separable, right? Yeah. So yeah, you can do that if you like. Yeah, but here we intentionally want to practice that exact ODE method. Exact. Yeah. Practice. Yeah. Yeah. All right. Yeah. So let's try that. Yeah. So we write it as this differential form before we can check if it has exactness. Yeah. Remember the criterion for that exactness. Yeah. So we want to check it. Yeah. All right. Now let's apply this criteria, this equality we use to check it for exactness. Yeah. Plug in the numbers, functions, m function, n function is just one, right? Yeah. Yeah. So for partial derivative of m over y variable, you get 110. The second one, partial derivative, 0. Yeah, because constant 1, you take partial derivative, you get 0. Not equal. Not equal. Okay? Yeah. So it's not exact. Exactness checking fails. So we cannot apply directly. Yeah. Yeah. But don't give up, because we have the experience. Remember, when we work on a separable ODEs, we can do substitution to convert some non-separable ODEs to separable ODEs, right? So we have chance to do some more work to, make it separable. That's for the, previous example. Here, the question, can we do some more work to make it exact form, the exact differential form? Yeah. Yeah. So there is a hope. Yeah. Interesting. Yeah. So let's go to the next step. Yeah. So the next step, reduction to exact form by integrating factors. There is another concept called integrating factors. Yeah. So this concept does some magic, helping us, converting non-exact form to exact form. Yeah. Yeah. All right, so let me show you how to do it. Consider the differential form, a general one. Here we use, yeah. So you may ask me, in this one, why we use P, Q symbol? The previous differential form we use M and N, right? Yeah. So why you make that change? Yeah. The reason pretty simple. Yeah. P and Q, when we use these two symbols, we expect this form is not exact. Okay? Then we multiply another function called integrating factor on them to make the form, differential form, exact. After we make it exact, then we use M and N. How about that? Yeah? Because here we need to use two pair of functions. Okay? First pair, PQ pair. Second pair, after we multiply a special integrating factor F function, capital F function, another pair we call M and N pair. Yeah. Try to separate. Otherwise, you cannot use same symbol for two different pairs. Yeah. So that reason. So we intentionally use different symbols. Yeah. Now, our assumption is it is not satisfied. Okay? Our criteria for the exactness is not satisfied. Yeah. So we need to do some more work to make it satisfied. Okay? Yeah. So next step. Yeah, let's look at a simple, interesting example. Yeah. That's example very simple. Yeah. We can easily see what's going on, yeah, and understand the basic idea. Solve this differential equation. It's a simple differential form. Yeah. M simple, N simple. Let's check. Yeah. Partial P over partial Y, -1. Partial Q over partial X equals +1. They are different. Okay? Yeah. Yeah. So this one, now we want to do some magic here. Okay? Do some smart manipulation here. So that critical manipulation step, yeah. New idea. This time we multiply a special factor. Multiply the original equation by this special factor, 1 over x squared. Okay? Yeah. You may ask me why you choose 1 over x squared, right? Yeah. Yeah. Later we will calculate it. We will find a way. Here I just want to make the point. Okay? Just show you the, you know, the basic idea. Yeah. Later, yeah, we will develop some systematic method to find integrating factors. Yeah. So this one, the so-called integrating factors. Yeah. All right. After the multiplication, yeah. So here you may see you multiply some factor both sides of the equation. It looks like you do some redundant work, right? You do not use the simplest form, right? Yeah, because this form is not the simplest. That one is the simplest, right? That one looks simpler than this new form. Yeah, yeah. So here we should have, you know, in problem solving. Yeah, here. Yeah, let me tell you my experience. You know, when we do problem solving. Yeah. So many times, the simplest form may not be the best. Yeah. Although it's simple, yeah, simpler. Yeah, people like the simplest form, right? Yeah, because some property is hidden by the simplest form. Okay. If your simplest form, some special critical property is hidden. You cannot discover. Yeah, some simple critical property. So in that situation, we would rather add some extra, it looks like redundant things, but because we change the structure. After we add something you may feel redundant at the beginning, but after we do that, the structure of this differential equation has completely changed. Yeah, changed. The structure is changed. We know structure is important. In problem solving, the structure is very important. Here, we want to take advantage of the new structure. After that change, now you check the, you know, exactness criterion this time, you get something different. Partial derivative this time, yeah, so if you still use partial PQ, it's okay, yeah, so yeah, partial MN, you know, yeah, still okay. This time you take partial derivative, both sides, you get the same expression, -1 over x squared. Yeah. It's pretty easy to see it. Yeah. Partial derivative. Yeah. That's what we need. Yeah. So this time we don't mind redundancy, right? Yeah. We like the redundancy this time. It helps a lot. Okay. Yeah, because it helps us change the structures. Then we have new properties. So we can take advantage of the new properties. And this time, the new differential equation, it's equivalent with the old one, right? Equivalent. Yeah. But one little thing you may need to consider, x cannot be equal to 0. Okay? The only small difference, yeah. X for the second form, x cannot be 0. Yeah. So that means after you find a solution, if you go back to the original one, you need to check x equals 0. That case, yeah. Do some extra work, yeah, to fix it. Yeah. Other than that, equivalent. These two forms, equivalent. So you can solve the second one first. Yeah. All right. Now, second one to solve, we have formulas to solve it. Okay? Yeah. So here, yeah, I skip calculation part. Yeah. All right. Yeah. Here. Yeah. So there is one thing I like to make, comment a little bit. Yeah. Because in our previous a few slides, I skipped several things. Right? I asked you to complete the solutions. Yeah. So I noticed that. Yeah. Yeah, I don't know how hard for you to complete those solutions correctly or not. Yeah. Yeah. I may like to do one thing. Yeah. Yeah, because I noticed many of you may not be familiar with some basic operations, right? Yeah. Including the algebra operations, derivative. Yeah, probably you do better, but integrals, I feel it's a hard part for you. Yeah. So I'm thinking about, I try to work on some, basic simple calculation examples, but every time I make the, formula change, I will specify what rules I apply. Okay, yeah. So I put one side based on, some rule. Yeah. So then I get this step. Then I go to another step, based on some basic laws or rules, whatever. In that way, I make a document like that. So you study, try to, compare, very basic things, algebra, laws, differential, derivative rules, integral formulas. I just, left-hand side, right-hand side. Okay, 2-column version. So, you can study those basics. Yeah. So in class, I want to save some time. In class, I do not talk about calculation details. Okay, yeah. So, but that document for each module, I make one document. Yeah, one PDF files. Those questions I didn't provide details in class, I can do there. Okay? Yeah. So try to help you. So then, another thing I'm also thinking about, in your homework assignment, I want to check your familiarity with the basic formulas. Yeah. Yeah. So my original plan, each homework assignment, 20 questions. Yeah. 20 questions, for the material, in this class. Yeah. But 20 questions, each one I like to give 4 points. Yeah. So 20 times 4, 80 points. Yeah. Still, we have 20 points to get 100 points. Yeah. So I'm thinking about make that remaining 20 points, checking your familiarity with the basic laws, okay? Algebra, simple questions, but get yourself familiar with those basic laws, integrals, derivatives, simple questions. But just you need to do some work, okay? You need to familiar with yourselves on those basic math, yeah? So using that chance to help you practice, at least you practice, 20 points, yeah? Then total 100 points, yeah, for homework assignments. Yeah. All right, so let's try that way, yeah. So this time, back to our original question. We need to find integrating factors. Yeah, something like this one. Okay, yeah. All right. Now we work on the general form. This time we multiply an unknown function f. Unknown. Yeah, because we need to determine its formula. We want to calculate it. Okay, so we put that unknown f. Yeah. Then we apply the exactness criterion, yeah, set up differential equation like this. Yeah. We hope we try to derive this formula from this equation. Yeah. Hopefully. Yeah. All right. So let's simplify. Yeah. We need to apply product rule, right? Derivative product rule. Left-hand side, right-hand side, the product rule of the derivatives. Yeah. So based on that, yeah. Here I hope you know the notation. Partial derivative, there is another simpler notation. Use the subscript. F sub y means partial f over partial y. Yeah. I hope you have seen it. All right, because it's simpler, right? You do not need to write, partial fraction, yeah, simpler, yeah. So many people like this way, okay, yeah. So this time, let's use the simpler version, yeah. All right, so product rule, partial f over partial y, yeah, times p plus f times p sub y, right-hand side. But if you look at this equation, how hard it is to solve for f. Given p and q, how hard it is to solve for f. It looks not easy, right? Yeah. All four terms, yeah, you have four terms. All four terms, you have f unknown. F is unknown. And f sub y, f sub x, all unknown. How do you do the calculation? Yeah. It's hard. Okay? Yeah. So, not just you, I feel hard. Okay? I do not know how to solve myself. It's hard for me. Okay? Yeah. In this situation, what should we do? Do you have an idea? In this situation, yeah. Now, we are in a special situation. Yeah. We had the similar situation before. Yeah. Anyone remember under this situation, what should we do? We did that before. Okay, if you can recall a little bit. Anyone? This is not the first time. Something, yeah, let me describe. Something relatively hard. If we work on it directly, we do not know how to do it. In that situation, there is one special strategy. What's that strategy we can do? Great. That's the one. Okay? Yeah. The author of this book called the Golden Rule. Remember the Golden Rule? Yeah. So when you have something hard to do, find a simpler case to do. simpler case. And also I refer to a famous educator, Polya. Remember how to solve, okay? That one. Yeah, that strategy. Simple, effective. Here, it's hard, so our strategy, because we have freedom to choose F, right? Yeah, we have a lot of freedom to choose F. Can we use that freedom? Yeah, that important freedom. So we intentionally choose some simple F functions. Simple F functions. No. We don't want it too hard. So we want it simple so that we can make this formula simpler. Then we have a chance to solve it. Yeah. Here, let me give you two simple cases. We can, make it much easier. Yeah. So what's that? The first one. Yeah. First one, we let F as a function of X. No Y. Okay? No Y in F function. That's simpler, right? Single variable function. Single variable function. Yeah. So sometimes we call univariate. Yeah. F is the univariate function, one variable. Yeah. No Y. If no Y, then you take partial derivative on Y, it's 0. Okay? Yeah. F sub Y, it becomes 0. So this term is gone. Okay? Okay? Then at least one term is gone. Okay? One term is gone. Yeah. See? Yeah. All right. Now we simplify it. Yeah. Yeah. So this time F prime with respect to X. So we can write prime. Okay? Yeah. All right. If with respect to Y, we do not use prime. Okay? Otherwise confused. So the prime case, that's with respect to the original variable. Yeah. So not a function, because Y corresponds to the the function part, not the variable part. Yeah. Only with respect to the original variable, we use that prime. Otherwise, we get confused. Okay? When you use prime, what's the meaning? Yeah. Here, partial F over partial X, we can write it as prime, because partial here, partial is gone, right? Yeah, because just that's our usual understanding of F prime. Usual understanding of F prime. Okay? All right. Yeah. So we get the simpler form. Yeah. Dividing FQ both sides. Yeah. So we want to see it better, see the structure better. So we do this division. FQ. Yeah. Yeah. To do this, we need some experience. Yeah. So you need to have some experience. Okay? So when you work on many similar questions, gradually you will have more and more experience. Yeah. Here, we need to do this special operation. After that, then this new form more friendly for us. More friendly. Why? The left-hand side, F prime over F. Remember, F unknown. Left-hand side, everything is unknown. F prime over F, unknown. Right-hand side, everything is known, right? P function known, Q function known, partial derivative, P, Q, all known. Okay? So the right-hand side, the whole function, whatever it is, we have the specific formula for it. Okay? Then we can solve for F. How about that? We can solve for F. Yeah. All right? So, yeah. So pretty much we find a solution. Pretty much we find a solution, but still one little thing missing, one little thing. Yeah. So what's that? All right. Yeah. Here in problem solving, observation is very important. Yeah. You need to try to, practice your observation to catch important details. A good problem solver, you need to pay attention to the details. Some details very critical. Yeah. So practice yourself. Yeah. Yeah. When you do observation here, look at the left-hand side. Remember, f it's a function of x, only x. So its derivative also another function of x, right? Yeah. So f prime over f, is it function only contains x? No y, right? Left-hand side, no y. Yeah, that's important. Right-hand side, not necessarily no y, right? Yeah. Sometimes you may have y. Yeah. How do you know right-hand side you can cancel out or y? Y-related terms. How do you know you can cancel out? Only when you are very lucky you can cancel out. Otherwise, in general, you may not be able to cancel. Why? Then it looks ridiculous. Left-hand side, it's a function of x. Right-hand side, you have a function with x and a y. How can that happen? It cannot happen, right? Yeah. So not compatible, so we treat. So this equality, not compatible. You cannot make it. We wish to have this equality, but we couldn't because they're not compatible. Okay? Yeah. In that case, this method fails. All right? Fails. Drop it. Yeah. Because we simplify too much. This assumption, we simplify, so we only consider this structure, but this structure, unfortunately, it fails. Yeah. Okay? Yeah. So you can try, but not necessary. You can make it. Yeah. Not necessary. Okay? Yeah. All right. Yeah. Here, let's introduce a function r equals this one. We do calculation. If, after we do simplification, if we see this function does not contain y, then this method works. That method works, so we can find f formula. Then the whole method works. So you need to check it. Check it. All right? Yeah. Excuse me. All right. Next, yeah. So you get this simple differential equation to solve. Yeah. All right. Yeah. All right. So next question. How do you know f is a function of x? Right? How do you know? Yeah. So it may not be true. Yeah. So based on, on some reasonable logic reasoning, f could be a function of y, right? Yeah. Still univariate function, but it's also possible f could be a function of y. Yeah. So let's do the similar work for x equals for y. Yeah. So here you can find, f expression from this simple equation. Yeah. All right. But here I want to do a version for f is a function of y. Yeah. Then, the details similar to our first case. Yeah. Divide fp, this time we get a slightly different expression. Yeah. Left-hand side, it's a function of y. Right-hand side, we don't know if it is a function of y or if it contains x terms there. We don't know. Yeah. But we can try it, right? Yeah. So here we introduce a different symbol, r star. We calculate to see if it has X terms in it or not. Okay? Yeah. If not, yeah, we are lucky, so we can solve this equation for F. Yeah. And the F formula can be represented explicitly by this formula. Okay? Yeah. So this tells us we can try two special F structures, yeah, both univariate structure, single variable univariate structure. Okay? Yeah. We wish one of the two works. Okay. If not, these two methods fail, yeah, then we may have chance to, find other different methods. Okay? Yeah. All right, take a break. Yeah, 10-minute break.